everyone. My name is Juntao. I come from Rutgers University. I'm happy today to present this paper called LLM-RecSys alignment with textual ID learning. So this paper is about how to better represent atoms in a text-to-text based generative recommendation style. So before start, I'd like to introduce some background. Right now, generative AI based on large language models is really trending right now. And where LLM takes the input of a sequence of tokens and directly predict the next token. And of course, you can predict you can also predict the following tokens autoregressively. And the pre-trained language model is very powerful, and they have a lot of good properties. So it's not too hard to think about whether we can use this generative style and apply it on recommendation scenario. So this is sort of the LLM-based generative recommendation model looks like. So we can convert the user interaction history into a natural sentence, and then we train LLM to directly predict next atom, but also in a text format. You can use any language model here, but if they are open source, then you can train it. But one big challenge here is how to represent the atoms in the text format. Like here, we have these atoms XXX, but what are these XX really are? So this is not an easy question because for NLP tasks, no matter you're doing machine translation or question answering or summarization, they are inherently operate on human vocabulary. So that means whatever you're doing, they only perform on a finite set of language tokens. That's kind of the reason why after pre-training a large language model and maybe aid some instruction fine-tuning, they can directly perform very well on downstream tasks. Because the context information learned are shared during this between these common tokens. But for recommendation, it's another problem because the atoms in recommender system, they are not natural language, they are entities. And even worse, the entity size is ever growing, like we have new atoms always come in. So it's not easy to pre-train a large language model for generative recommendation. And how to appropriately encode those atoms in natural language is very crucial. One way is natural way to represent entities in language is to use some special out-of-vocabulary tokens for the atoms. Like here, for this user history, we can use 3 numerical numbers in this angle bracket. So there are some special tokens that never seen and don't exist in the vocabulary. And in this way, we can integrate those special tokens into the natural language. So we can compose the training set and directly train this language model to predict the correct recommendation. This is something already been done, and the performance is not bad. But there are a lot of limitations here. First, the biggest advantage of using language model is the pre-training. We learn a lot of information during pre-training. But now, if you are representing each atom as a special token, we are basically almost throwing away all the information learned during pre-training. So there are some new tokens. And those old tokens are meaningless. So imagine that if you train this model, it seems like you are learning something text-to-text. But essentially, you are learning some dense embedding vectors for those special tokens. So it's like we are learning k-value pairs. So and it goes back to the classical recommender system. Typically we learn user embedding, atom embedding, we compute the similarity scores, right? So this is something similar. In this way, we are learning these old tokens and they are non-transferable. If you train this large language model in one data set, it's not going to work on another data set. You have to retrain another one. So we lose another advantage of using large language model. And because of this observation, in this paper, I'm thinking that some desired properties for the atom IDs, for the atom encodings, should have those properties. First, they should be unique and concise because they should be easily, uniquely identified atoms. But also, they should be semantically rich and platform agnostic. And because of this reason, I think the better way is to representing atoms in human language tokens. And in this paper, we call them textual IDs. So this is how the textual ID looks like. You have some, for each atom, we have a lot of descriptions. And we do like minimal pre-processing to convert them into plain text. And no matter the information used for or noise, we include everything here. And we train an ID generator, we introduce an ID generator, like take input of the atom plain text and directly generate some keywords, some human language, and to like as the textual ID for this atom. And we generate the textual ID autoregressively. And this ID generator is like a universal model. You can apply on any atom, no matter which data set it comes from. And here I show examples from, of two atoms come from different data sets. You see we can learn some keywords here. And with this ID generator, I think a better generative recognition structure can be something look like this. So we have user history. And for each atom from user history, we input their plain text, and the plain text goes through the ID generator and convert it into some keywords, some textual IDs. And those textual IDs are going to blend with natural language sentence. And then we can train a generative recognition model based on LLM. And the input of this model is also textual ID. And this ID is also generated from the ID generator. So it has two parts. The ID generator and the base recommender, they are both LLMs, and they work separately, and they can be trained separately. And imagine that you have an ID generator, you can generate IDs for all the atoms all at once. Then you can train the base recommender system to learn to predict the character recognition. And for training the ID generator, we're going to fix the base recommender and only train the ID generator to generate the IDs that can best describe the atom from a recognition perspective. So, one thing is like, it's kind of like a chicken and egg problem, so you need a good start. And the good start comes from, you say they generated IDs for each atom is kind of like some tags. So we start of training this model, we choose a pre-trained model for a new tag generation. And start from that, we fine-tune it to gradually learn to generate like some IDs that's suitable for recognition purpose. And training this model is not too hard. We include all the training details in the paper. But now I'm going to talk about two of the most important details. The first one is, say you have an ID generator, you can generate ID for any incoming atoms, but the ID should be unique because they are also used for retrieval. You have to retrieve the atom. So we introduced a diverse ID generation algorithm based on something called diverse beam search. So this is very simple. You just generate K candidate IDs, and with a length limit, we want them to be short. And you just select the first unique one, and that will be the ID for this atom. However, if after going all the K group IDs, we don't find a unique one, they are all existing in the database, then we increase the diverse penalty and try again. If fail after certain tries, in the paper I believe is 5, after certain tries, we can include the length limit, so you generate a longer ID, it's going to be unique once again. So during experiments, we tried to generate IDs for more than 200,000 atoms, and only 10% of them need a second try to generate unique ID, and about 4% of them need to increase the length to make them unique. And another thing is about the alternate training schedule. So we are like alternatively training the ID generator and base recommender, and each of them train different epochs. So these type of parameters are different for different experiment settings. I'm going to mention more later. The first is direct training and testing. So this is a standard sequential recognition testing. You train the model and test the model on the same data set. For this setting, we train 3 iterations, and for each iteration, we train the ID generator for 1 epoch and train the base recognition for 10 epochs. And another setting is we treat this model as a foundation recognition model. We collect the recognition records aggregator from the internet, and we have a huge pre-training set, and we train this model. After training, we do zero-shot testing on new data set. for that part, we found that you only need to train the ID generator and the base recommendation model for only one epoch, and the further training gonna lead to overfitting and hurt the performance. And this is the results on standard task. And we see that this paper is performed really well. And especially you compare to other like generative recommendation models based on numerical IDs. This textual ID is very powerful and perform really well. And these are just numbers. We really want to see like how the generated ID looks like. So here I include some example here. For this atom, like initially we have an ID generator pre-trained on news tag generation. It's going to generate the blue part, these IDs. So there are some words, but like kind of selecting the first few words from the plain text, they are not very informative. But after a few rounds of training, we see that the generated ID is really, okay, I'm going to wrap up first. It's really informative, and I don't even need to look into the original description. I just need to look into the generated IDs. I have a good sense about what this atom is about. And this is another example for this restaurant. The initial ID is just the restaurant name, but after fine-tuning, they ate like a cocktail, bars, taps, so that's a very interesting ID generated. And we have tons of these examples in the paper. So another thing is like, say, training this model, we don't need any like in-domain IDs. All the IDs are in human language. That means the recommendation recommendation data points are decoupled from the original data set. If you are like think about if you are the model, you don't need to care about like this recommendation, which data set this user history comes from. Right? They can come from everywhere. So that means theoretically, we can start collecting recommendation data from all the data sets like available, and we can compose them as a fusion data set. And I call it massive recommendation corpus. We can train this model on this fusion data set only for one epoch, then we can do zero-shot testing. And here, for these experiments, I collect a lot of data from Amazon review data set. I only exclude a few of them for zero-shot testing. And we can see the result is, it's not like outperforming all the supervised methods, but it's still very good, especially like there are not many recommendation models like focused on zero-shot testing. We compare to one of the state-of-the-art model, and we see like for most metrics we are outperforming it, and especially for the inter-platform test, which means this Yelp dataset, this Yelp dataset is a new platform that not exist in the pre-training set. So for this cross-platform test, we see this model is very flexible and adaptive. So there can be a lot of future works, and I list some here. Like you can always try larger model, because in this paper I use a really small model. It's called like a large language model, but it's just T5. And you can try a larger model, more data, and different admin encoding structures, and of course for practice for industry we can do more studies on scalability. And you can have a lot of future directions instead of those I write here. So thank you. This is our paper. I hope it makes sense to you.